Okay, and so last time we went through the whole method for how do we solve a linear constant coefficient difference equation in order to perform system analysis, which is taking a difference equation as our description of our system and given an analytical expression that describes the input, we need to come up with a function of n, an analytical expression for the output y of n. And the problem we solved was this one, where we had this first order linear constant coefficient difference equation with one initial condition. And it was for a recursive system that was linear and shift invariant and causal. And we applied a big unit step to it, a 2u of t to it, and wanted to know what was the total output of the system that's made up of a zero input response and a zero state response, or a forced response and a natural response. And we went through the process and used that as an illustration for how we go through the process of solving a linear constant coefficient difference equation like this. And we went through finding the zero input response, where we found the form of the natural response from the roots of the characteristic equation of the system, put an unknown coefficient in with that, used the initial conditions to solve for that unknown coefficient. And because the zero input response was the response of the system to those initial conditions. And then we went on to solve not the original difference equation, but a simplified version, the one we called the single input case, where we brought all of our y terms to one side to the left, and on the right, we eliminated anything that wasn't just x of n. We left just the single input, just x of n on the right side, in order to find the zero state response for that particular case. And we did that by finding a forced response first that took on the same functional form as the forcing function, the input signal. So we put a step in with a constant output after that step, and we got a forced response that had the same kind of step function followed by a constant value. And then we solved for the natural response component that was due to hitting the system with a new input by, again, taking the known form of the natural response that came from the characteristic equation, assigning an unknown coefficient to it, and then solving for that unknown coefficient using initial conditions, but not the initial conditions of the system that were driving the zero input response, but a special set of initial conditions that go with a zero state response, namely that we're in the zero state, that our system is relaxed, which means all the initial conditions are assumed to be zero. So with that assumption, we came up and solved the natural response component of the zero state response for the single input case. And then quickly at the end, we had to run through this a little bit too fast. So let me repeat what we did there. And that was, this is in fact the zero input response for that simplified version of the difference equation, which in our case was y of n plus 1/2 y of n minus 1 equals just x of n. We really want to know what's the response of this whole system that includes these other x of n terms. And to accomplish that, we applied linearity and shift invariance to say, if just x of n by itself produced this response that we called the zero state response for the single input case, if I had 2x of n on the right side of my difference equation, we would have gotten twice as much of this response. And if we had that response, if the input is delayed by one term, like it is in this x of n minus 1 term, then we'll get the exact same response, just delayed one place. So we replace all the n's with n minus 1s. And for this particular system, we didn't have any scale factors. We didn't have any multipliers on our x of n, so we didn't have to multiply our single input case zero state response, but we did have this other factor, this x of n minus 1. So if this was the response to just x of n, the response to a system that has x of n and x of n minus 1 to it is that same response from the x of n, and that response with n replaced by n minus 1 to get the response to the x of n minus 1 term. That's applying linearity and shift invariance. So that gave us the zero state response for the whole difference equation, the general case equation that includes both of these x terms. That's not the total response. For the total response, we still have to add in the response that came from the initial conditions, the zero input response. And so we added that zero input response, the -1 times -1/2 to the nu of n, to our zero state response from the general case. And the only term that changed was this one here, where we had a -1/2 to the nu of n. From the zero input response, we had a -1 times that. From the zero state response, we had +2/3 times that. So together they gave us a total of -1/3 times that, and all the other terms came along to the total response. So this would be what the whole system would do. Given that input, this set of initial conditions, this is the total response. That's what we were looking for coming up with this particular problem. And notice this total response has two different shaped functions in it. One that's a unit step or delayed version of a unit step that resembles the input. So these in green, these two terms, we would consider the forced response of the total system. And all the terms that have the same functional form, the -1/2 to the nu of n that came from our characteristic equation, we would say these together would be the total natural response of the system. So that's what we came up with this particular example. And the method that we followed there is the one that we can apply to solve any linear constant coefficient difference equation, with two exceptions. There are two special cases, two particular kinds of inputs and two particular kinds of characteristic equations where we have to change one or two places in the process. So before we get to those exceptions, let me just pause and let you all ask any questions you have about this particular process, the process we went through on Monday and today to come up with a total response, finding the zero input response, finding the single input case, finding the single input case forced response and natural response, to find the single input case zero state response, then generalizing that to the general case zero state response, and then adding those, the general case zero state response to the zero input response to get the total response.
So the areas in green, we would consider that was the forced response?
Right. For these kind of inputs, the forced response has the same basic shape, the same functional form as the input signal. So we have a unit step input, we got a unit step in two places in the part of the response. So those are, we would assign those as what came from the forced response. And actually we can see it too directly. Here was the forced response component when we solved for the single input case zero state response. So that's definitely part of the forced response. And when we generalized the zero state response, this other component came from that generalizing of this term. So by either of those two means, we would say, yeah, okay, these are the two parts that are the forced response, and the natural responses all have the same basic functional form, the -1/2 to the n, that exponential decay. Those are all the terms that have that shape would be the natural response.
And then you use the initial conditions to find the response, right?
We use the initial conditions to find the zero input response. The forced response we found by plugging in our assumption about what the shape of the forced response was based on our input signal. We plugged that into the single input case difference equation because that input had to be a solution to that equation. And we set it equal to the actual input that we had. And that's what gave us the missing coefficients that we needed. We use initial conditions when we're solving for the coefficients on the natural response pieces, whether they're part of the zero input response or zero state response. For the zero input response, though, we use the initial conditions that go with the total problem because that's what we're finding, the response of the system to those initial conditions. The initial conditions we use when we're solving a zero state response are different. For those, we have to use initial conditions that are appropriate for a zero state, for a relaxed system. And so for those, we always set all the initial conditions equal to 0. So that's the tricky part we have to keep in mind when we're solving these kinds of problems. When do we use the real initial conditions? That's for the zero input response. For zero state response missing coefficients, we use 0 initial conditions. Well, there's actually a picture of what the input and output would be for that system, drawn not as a stem plot, but in a connect the dot kind of plot. So the blue is the step input. We go from 0 prior to n equals 0, jump up to 2, and stay there. And the system responded by doing this, what we would notice as sort of a decaying oscillation and settling into a value different than our system. And we have 4/3 from here and another 4/3 from there. So about 8/3 is where we're going to settle into here. And we've got a little bit of oscillation going on back and forth. And although we don't see it because we're not zoomed in far enough, this is a recursive system. It is actually an infinite impulse response system. And so these little dots are actually wiggling up and down around that line very slightly with a decaying amount as we go forward. So we would consider this a stable system. It's a little bit underdamped, but certainly stable because it does kind of converge to a finite level there when given a step input. Now, what about these special cases? Well, there's two instances where we're going to make changes to how we do that process that we went through on Monday, where we have to tweak the process a little bit. And the first of those is if our input signal, x sub n, happens to have the same functional form as one of the terms that's existing in the natural response of the system. And again, those terms came from the roots of the characteristic equation. So for example, we found the characteristic equation system included a z equals 1/4. So our natural response has some unknown coefficient times 1/4 to the n and maybe some other terms. And to that particular system, I'm applying an input that's also a 1/4 to the n u of n. Well, if in that case, then I have to change my assumption around what the input signal's forced response is going to be. And we go back to our table that we use for determining for some input function, what's the form of the forced response. There's some fine print here. There's a couple of asterisks that we have to go read the fine print. And those asterisks say, for entries that include exponential terms, alpha to the n, for our forcing function, for our input, that's these guys with asterisks, if the alpha is also a root of the characteristic equation, so meaning I'm, as in that example, if I'm driving it with a exponential function and that exponential function also appears as part of the natural response of the system because of its characteristic equation, then I have to change my assumption about what the forced response is going to be. If I had a real exponential input, we would normally say that the form of the forced response should be some unknown coefficient, c times alpha to the n. But if we have a case where this alpha matches one of the terms in the natural response, I have to add an n into the system. And if for some reason that alpha to the n is a multiple root of the characteristic equation, I might have to actually raise n to some power, which is what the rest of this alludes to. If that root of the characteristic equation is repeated p times, then the forced response gets multiplied by n raised to the p power. Now we'll get more into what we mean by repeated roots of the characteristic equation in the next example. Let's just take this with a simpler example where this input, an input matches our natural response of our system. And we'll stick with the same example we went through yesterday, or excuse me, on Monday. Same difference equation, same initial conditions, but I'm going to change up the input. Instead of putting in a big unit step, the 2u of n, we're going to put in a minus 1/2 to the n u of n, a decaying oscillating exponential function. And if you recall from that solution, the natural response of this system, of that first order system, had the form of k times minus 1/2 to the n, because minus 1/2 was a root of the characteristic equation of the system. And so this now invokes this special case. I have a minus 1/2 to the n in my natural response, and I'm hitting the system with that same input. So how does that change our process? So instead of solving this problem that we did originally, where our input was 2u of n for some initial conditions, we got a certain zero input response, we found a single input case zero state response, and so on. The only part of the process that's going to change, the zero input response, is going to be the same when I change the input. What's going to change is our assumption about the forced response. And so then perhaps the natural response may change as well. So if I pose the same problem with the same difference equation, I keep the same initial conditions and just change the input, The zero input response doesn't change because it's the same system driven by the same initial conditions. So we can assume, we jump to the conclusion that that is the zero input response for the system, the same one we arrived at in the example last time. This time, though, what's going to change again is our forced response, and therefore the coefficients that go with our natural response. The form of the natural response doesn't change, but definitely the form of the forced response is going to change. Now, because I'm overlapping a term in the natural response, I need a different function for my forced response. And our table says, well, if I'm driving with a minus 1/2 to the n, that's an alpha to the n kind of exponential function. Instead of my assumption being that the forced response is going to be some c times minus 1/2 to the n, I have to multiply it by n. Now let's take that through. Let's go through that example and see how that would work out numerically. So we have our same problem that we had before. We have our difference equation that was y of n plus 1/2 y of n minus 1 equals x of n plus x of n minus 1. We had our initial conditions, y of minus 1 equals plus 2. But now our input is changing. It's going to be 1 times minus 1/2 to the n times u of n. And we said the zero input response is the same because our initial condition is the same. So we don't need to attack that. For the zero state response, though, for the single input case, we're still working with the simpler equation, y of n plus 1/2 y of n minus 1 equals x of n. That's our single input case. And we go after that by first finding the forced response. And for x of n equals to minus 1/2 to the n u of n, we would look that up in the table, and normally that would lead us to the assumption that the forced response in the table would say it's the same function, minus 1/2 to the n, multiplied by some unknown coefficient. Unfortunately, though, we know this is a system that has a natural response that has that same form. And because of that, we have to change our assumption about the forced response. We have to, in this case, multiply the whole thing by n. And that's what makes this one a special case. The rest of the solution method goes exactly the same way it does before. We change our assumption and go through the same steps that we would have for solving this equation. So we would have plugged this into the single input case difference equation that said y of f and 1/2 y forced of n, n minus 1. That's equals our actual x of n. And we'll go back to black so we can see that more clearly. Well, here's our assumed yf is c times n times minus 1/2 to the n plus 1/2 y of f. The forced response at n minus 1 is the same as taking our y of f over here. And everywhere there's an n, we have to replace it with n minus 1. So this would be a c times the quantity n minus 1 times minus 1/2 raised to the n minus 1 power. And that equals to x of n, which we said is minus 1/2 to the n u of n. So we'll put a minus 1/2 to the n over on either side. All right, so everybody see, so we just plugged in our new assumption for the forced response into the single input case difference equation. There's our y of f, there's our y of f of n minus 1 equals x of n. And now let's do a little algebraic simplification. I'll keep that first term there unchanged. We have 1/2. We still have c times n minus 1. And this minus 1/2 to the n minus 1, I'm going to break up into two components. We'll make that minus 1/2 to the n times minus 1/2 to the minus 1. Whole thing still equals minus 1/2 to the n. And now we're trying to solve for c. So I want to isolate c equals some numeric constant. I've got a lot of minus 1/2 to the n terms I'm going to try to factor out. In fact, I see that I can already. I've got one here, I've got one here, I've got one here. And so if we strike all those out, then I have that Cn from this term plus 1/2 times C times n minus 1. And we still have this minus 1/2 to the minus 1 power, which happens to be minus 2, because with the minus 1 we flip it over. And all we have on the other side is 1, since we canceled that one out. And our minus 2 times 1/2 gives us a minus 1. So we have a Cn minus Cn plus C equals 1. So therefore, C must be 1. And our forced response then, our C is 1, and still times minus 1/2 to the n. So we just went through the process the same way we would have with solving a forced response. We just changed our assumption about what shape it has. And we got a little bit more algebra to work with, but that's not too bad. We're not done with the single input case zero state response, though. We still have to do the natural response part.
Hey, Professor, I had a question. For
Sure.
the force response, it keeps the N, right? You had a red N for the force response, and you didn't write it in green?
So yes, the N, oh, yes, you're right. In the green, I missed it. That's very important. Thank you. Okay, so going back to find the total zero state response for the single input case, we're going to add the forced response that we just figured out to a natural response piece with unknown coefficients. So we'll take our 1 times n times minus 1/2 to the n. And you're right, that would have been very problematic if we didn't have that n with us. Put our k2 times minus 1/2 to the n, our known form of the natural response with an unknown coefficient on it. And we'll use our one initial condition. The zero state response at n equals minus 1 has to be 0. And so if we plug in n equals minus 1, we'll have 1 times minus 1 times minus 1/2 to the minus 1 plus k2 times minus 1/2 to the minus 1. And so 0 equals the minus 1/2 flips over to become minus 2 multiplied by minus 1 gives us a plus 2. And this becomes minus 2k2 equals 0. So therefore our k2 turns out to be plus 1. And we have our total zero state response for the single input case. There was our forced response, 1 times n times minus 1/2 to the n. And our natural response, which was our k2, this is 1 times minus 1/2 to the n. And that's all for n greater than or equal to 0. So I can put a u of n there to tell us that it starts. It doesn't start before that input starts, so it can be multiplied by u of n to start it at n equals 0. And so different than we had before, since we had a different forcing function, the rest of the problem would go forward the same way that it did originally. First, we would have to find the general case zero state response, which for this particular system would have been putting back in the x of n minus 1 term. So that would have been the yzs 1 of n added to a delayed version of that. So we would have taken this and then made another one, 1 times n minus 1, minus 1/2 to the n minus 1, plus 1 times minus 1/2 to the n minus 1, all times u of n minus 1. Added it to this to get our zero state response to the general case. And then the total response would have been that zero state response for the general case added to the zero input response that we had computed before, and we'd have the total response. So for this special case, the only thing that changed was our assumption for the form of the forced response. Without the special case, this input would have generated a forced response of c times minus 1/2 to the n. But since this was the same as one of the terms of the natural response, we had to add the n to it. And here, as it turns out, is what that output would have looked like. The blue, again, is the input signal, a decaying oscillation. It's decaying because it's 1/2 to the n. It's oscillating because of the minus 1. So it's positive, then negative, then positive, then negative, then positive, then negative. So that's what we put in was the blue, and the green was the response. It gave us a natural response that has the same kind of exponential decay, the same kind of oscillation frequency, except it's multiplied by that n, so that exaggerates it a little bit. Okay, so that's the first special case. The second is what happens when the characteristic equation has repeated roots. Like if this was our characteristic equation, z squared plus z plus 1/4 equals 0, that happens to be a perfect square. So there would be 2 roots of this characteristic equation, and they both would be the same. So we would call these repeated roots. Well, that's going to change the nature of our assumption about the natural response shape of the system, right? So when we had distinct real roots, we were operating up here on the table where this was the form of our roots of our characteristic equation, and this side gave us the form of the natural response. So when we had just plain minus 1/2 to the n, only one of them, we said the natural response must be k times minus 1/2 to the n. If we have 2 of them, though, we have repeated roots, and so we'll have one of them be the same. We'll have a k0 times minus 1/2 to the n. But if there's 2 of them, I'm going to have another term that's k1 times n times the minus 1/2 to the n. And if it repeats 3 times, if we have 3 roots that are the same, I'll have the same thing with an n squared term. So k2 times n squared times minus 1/2 to the n, and so on. So we say if the root appears p plus 1 times, so if it appears twice, p must be 1. We include terms in this expression all the way up to the n to the p term. So if p equals 1, I would only go up to n equals 1. If there's 3 roots that are the same, p is 2, and I would get a 0, n equals 1, and n squared term. Okay? So rather than use our more complicated example that we've been using all along, let's illustrate this particular special case with a simpler example. Here's a second order system, so I guess you wouldn't say it's simpler in that sense. It's a higher order system, but we're going to use a single input case difference equation. So we don't have to worry about generalizing zero state responses. Take that step away. And we'll put a simple unit step in, which will not match one of the roots of the characteristic equation, so we won't have to worry about that special case. And I'm going to start the system off relaxed. All the initial conditions will be 0, so there will be no zero input response either. Now this is a second order system, so I need 2 initial conditions. They would be y of -2 and y of -1, and we're going to set them both equal to 0 to force the system to be relaxed. So I've eliminated the need to find a zero input response. I've eliminated the need to generalize a zero state response. We made it as simple as we can. A single input case, there is no zero input response, so all I have to do is find a forced response and the natural response part of the zero state response, and I'm done. And we'll keep it simple because, well, we've just complicated that natural response by invoking this special case. And we'll be in here using this part of the table in order to find our natural response. Let's go back to the whiteboard and see how that plays out. So here was our system, y of n minus y of n minus 1 plus 1/4 y of n minus 2 equals x of n. And our x of n was pretty simple. It was just a unit step. And our initial conditions, there were 2 of them, y of -2, y of -1. They both were 0, so we had a relaxed system. So we don't have to do a zero input response. That equals 0 because it's relaxed. So we go right to the zero state response. In this case, it is already a single input case, so we don't have to do anything fancy on that. So typically we would go after the forced response first. And we look at our input signal. Our x of n is a unit step, which is equal to 1 for n greater than or equal to 0. So we'll look that up in the table, and we would find that the forced response then is also a constant, some unknown constant c. We plug that into our difference equation. So y forced of n minus y forced of n minus 1 plus 1/4 y forced of n minus 2 equals our input x of n. And as we saw in our example last time, if my forcing function is a constant and my forced response is a constant, all of these terms, y of f and yf of n minus 1 and n minus 2 will all also be constants. So this is very simply c minus c plus 1/4 times c has to be our x of n that was a constant 1. And so c must be 4. And then our zero state response, which is the forced response plus a natural response piece. It's going to be that 4 that we just found, plus I need to know what the form of my natural response is. So, well, I guess we're going to have to go up and find that out. So let's go find our characteristic equation, which for this system looks like a 1. Looks like we have a minus 1 times z minus 1, and we have plus 1/4 times z to the minus 2 for this delay. And then we're finding the homogeneous solutions for setting that equal to 0. If I multiply everything through by z squared, get z squared plus, z squared minus. There we are. Z squared minus d squared minus c plus a quarter equals 0. And if you factored that, that's a perfect square. That's a z minus 1/2 quantity squared. So our z has two values, two roots of minus 1/2. I'm sorry, plus 1/2. So roots. And so our form of the natural response would normally be some k1 times positive 1/2 to the n, but I have two of them. So I have k2 and a 1/2 to the n, but the second one, because it's a repeated root, gets the n out in front of it. And now that's the only part that changes in the way we're going to solve this problem. That's our assumption for what the form of the natural response is. And particularly this needing this extra n because they have a repeated root. The rest progresses the same way. We start with initial conditions, y of minus 1. In this case, it's relaxed, so, and because we're doing a zero state response, it also has to be 0. So that must be 4 plus k1 times 1/2 to the minus 1 plus k2 times minus 1, replacing n, and 1/2 to the minus 1, which is a 4 plus 2k1 minus 2k2. That equals to 0. The second initial condition, y of minus 2 has to be equal to 0. So that's 4 plus k1 times 1/2 to the minus 2 plus k2 times minus 2 times 1/2 to the minus 2, which simplifies to 4 plus 4k1 minus 8k2 equals 0. So we have two equations, two unknowns, and it turns out when you solve those, k2 turns out to be minus 1, k1 turns out to be minus 3. So our zero state response for the single input case is the same as the zero state response for the general case because we have a single input case equation. That's also the total response because there is no zero input response. In that case, it's 4 that we had from our forced response. We said k1 was minus 3, so minus 3 times 1/2 to the n, and k2 is minus 1, so minus 1 times n times 1/2 to the n, all times u of n, and that's our solution. So again, for all of the algebra we did here, the only thing that changed was our assumption about the form of the natural response that came from the fact that we had a repeated root. And again, we used this expression. We had two repeated roots, so we had a k times 1/2 to the n and a k1 times n times 1/2 to the n. What if we had double trouble? What if you had both special cases happening at once? What if we had that same difference equation we just solved with still relaxed, but I made my input 3 times 1/2 to the n with a u of n after that? I guess I should have that. Where I'm forcing it now with the same shape as not just one, but two terms in the natural response. What do I do in this case? Well, we do everything. We would assume our natural response still has the same two forms because it's a repeated root. It would still keep these two forms. But now my forced response would have to be some unknown coefficient c times 1/2 to the n multiplied by not n, but n squared. If we scroll back to our table there, where the fine print was, that was where this extra caveat was coming in. If that alpha to the n is a solution of the characteristic equation, a root of the characteristic equation, repeated p times, so in our example it was repeated twice, then the forced response should be multiplied by n to the p, or n squared. And so that's what we were suggesting would happen in this particular case. Let's see if I can get this to move forward to there. There we go. So if we were going to solve this problem, we would, for the forced response, we would assume yf was c times n squared 1/2 to the n. Solve for that, and then the natural response would still have this form, and we would solve it using the zero initial conditions as well. So they can work in tandem. That can happen. That's all the special cases we have to deal with. There is one additional complication that can come in. We've been using the simplest version of roots of our characteristic equation and inputs. We've been using either constant inputs or exponential inputs. We've been solving all problems that have exponential terms in their natural responses because we have real roots of their characteristic equations. But not all systems are like that. You can have roots of the characteristic equation that aren't just real, but we can have complex conjugate pairs, for example. And so what do we do then? Well, we just go to a different part of the table. But those kind of characteristic equations, those kind of natural responses are going to include an exponential term and cosines and sines. So the process doesn't change, just the assumptions we make, the forms of our natural responses will change. Likewise, if we drive our signal with a cosine, then, well, we'll have a cosine forced response. And so again, we'll get into some trigonometry and have to deal with slightly more complicated mathematics, but the process doesn't change. On Friday, we're going to come back and we will work on starting our next method of doing system analysis, namely, how do we perform convolution? And so in preparation for that, we'll have to revisit unit sample responses and find how to determine what those are analytically, not just by recursion, and then begin to learn how do we combine those analytical expressions for our unit sample response with the convolution process in the discrete time domain and revisit convolution and its basic concepts. And we'll start that next time.